A very good morning. My name is Oh Sun Yang, matrix number MA24103, and today I'm going to present regarding Six Sigma DMAIC. Okay, now we are walking through the core engine of process excellence, the Six Sigma DMAIC framework. And if you look at this visual roadmap, you'll see that DMAIC isn't just a set of instructions. It is an interconnected life cycle. It takes us from identifying a chaotic problem, systematically measuring it, isolating the root causes, and finally establishing an automated control loop. And the key takeaway here is simply by applying this structure loop, we replace guesswork with data-driven execution, directly boosting our baseline productivity and product year. Moving on to this slide, let's talk about the standard of quality we are actually aiming for. And the most important number on this screen is 99.999966%. Operating at a true Six Sigma level means near perfection. In practical manufacturing terms, we are talking about a limit of no more than 3.4 defects for every million opportunity we run on the line. Our goal here is not just occasionally success, it is just about reducing process variation so tightly that our output becomes highly predictable, consistent, and flawless every single day. And as shown as in this slide, this is our step-by-step pipeline. We measure by defining the scope and locking in customer targets. Next, we measure our current baseline performance to understand exactly where we stand. Then we analyze the data to separate the real root cause from mere symptom. In the improve phase, we deploy and pilot optimize fix. And finally, we control the new process so we never slip back into old habits. It's a continuous journey where every phase acts as foundation for the next. So now, how do we organize our teams to actually execute this? Think of black belts as our full-time project leaders who can handle cross-functional, high-complex systems. And while green belts are our operation practitioners, they balance daily engineering and manufacturing duties while leading the localized improvements. And finally, our yellow belts support data collection and local process mapping. Having this clear division of labor ensures every tier of the factory has a direct hand in our quality culture. And let's address a critical operational question. Out of hundreds of potential issues in a factory, how do we choose which project to tackle first? We use the two filters on this slide. First, customer alignment. The project must address a critical to quality parameter, meaning it must matter directly to the end customer. And second, feasibility. We look for projects with a clear financial return on investment (ROI) that our team can realistically execute within a tight 3 to 6 month window. If it doesn't align with the customer and it isn't feasibility, we don't run it. This keeps our efforts tightly targeted and incredibly high yielding. Okay, now we'll move on to the define phase. Moving into the define phase, our first absolute priority is locking down the project charter. Think of this as our official contract with the executive team. And on the left, we establish the strategic boundaries and baseline metrics to prevent scope creep down the line. On the right, we highlight our core pillar, the precise problem statement quantifying our current process pain, a clear business case justify our resources, and our ultimate goal statement, which is to aggressively push our defect rate from 12% baseline down to just 1.5% by the end of Q4. Next, to ensure everyone is looking at the same process from a bird's eye view, we deploy a cyborg map. This lets us align our perspective instantly. We map up our external suppliers and the critical inputs they inject, such as raw steel sheets or specific design tolerances. Those fit into our core 5 to 7 step process loop. And finally, we track our tangible outputs, in this case, our completed trace, and identify the immediate internal and external customer receiving team. This ensures that there are no blind spots regarding our process boundary. Data collection is meaningless if we don't align it with what our market actually cares about. These metrics show exactly how we translate the qualitative voice of the customer into internal engineering metrics. For instance, when a customer complains that a component breaks too easily during assembly, we don't just guess a fix. We translate that into a measurable, critical to quality CTQ target, especially setting our tensile fracture strength limit to greater than or equal to 450 MPa. Every customer complaint is converted into a clear, verifiable metric with an exact target specification. So one of the primary reasons engineering project fail is trying to fix the entire factory at once. To prevent that, we have drawn a hard line in the sand regarding project scope. Look at the green card on the left. Our team is strictly focusing on controllable variables, specifically the machining parameters on line 3, operating training for shift A and B, and our immediate steel tray thickness variances. Conversely, look at the red card on the right. Modifying vendor contracts, buying brand new laser equipment, or overhauling the warehouse logistics are strictly out of scope. This keeps our execution fast, target, and within our directly authorized. And to wrap up the define phase, I want to emphasize this critical warning on the left. Statistically, 50% of all process optimization projects fails before they even start, strictly due to poor initial definition. If you measure the wrong things or define your boundaries poorly, your improvement phase will yield zero real-world value. By locking down our problem statement, securing our business case, and clarifying our exact goal right now, we protect our resources and ensure this Six Sigma initiative delivers sustained, high-impact ROI rate of return. Okay, let's move on to the measure phase. Alright, moving straight into measure phase, our first operational milestone is floor level process mapping. But our precious cyborg gives us a high level view. Our action plan now demands that we talk the floor to capture how the process operates in the real world. We use structure value stream mapping or VSM section to physically track material travel distance, expose information hands-off delay, and flag accumulation zone where inventory sits in queues. By defining these targets, we clearly separate our true value added work from systematic waste. Before we can trust any data we collected, we must validate our measurement system using a gauge R&R analysis. This isolates the two major components of measurement errors. On the left, we look at repeatability, which measures tool precision, evaluating if a single operator gets the exact same value when measuring the same part multiple times. On the right, we evaluate productibility, which tracks appraisal variation across our shift. If different technicians use different methods or look at the dials differently, our data is corrupted. we must lock down both elements to ensure a clean baseline. And with a validated gauge system, we establish the concrete baseline performance profile you see in these metrics. Across our core process areas, the data reveals significant gaps. Our component assembly line is averaging a cycle time of 142 seconds, pushing us 18.4% over our target limit. Our metal bending line show a 6.2% defect yield on shear strength. Most critically, our procurement order entry look is generating a massive 88,000 defects per million opportunities. This metrics pinpoints exactly where our process stands today and establishes the baseline we are going to improve. As we manage this data, we split our findings into two categories shown here. On the left is continuous data, variable like assembly time, metal thickness, or fracture load. This data is highly preferred in engineering because it provides immense statistical power using relatively small sample size. And on the right is attribute data, which covers discrete counts like parts of fear metrics, while attributing data is simple to track. It requires much larger sample size to mathematically prove an improvement. Therefore, our primary diagnostic focus will remain on continuous parameter whenever possible. And to close out our measurement loop, we must evaluate our overall system capability using two Witter indices, CP and CPK. The top panel details our potential capability index, CP, which looks strictly at the raw spread of our process against engineering specification limits, completely ignoring centering. The lower panel highlights our demonstrated capability index, CPK, which accounts for real-world process shifting by measuring how close our actual mean is to the nearest specification edge. Together, these two metrics mathematically tells us whether our current equipment is truly capable of hitting our customer targets long term. Okay, now we'll talk about analyze phase. Moving into analyze phase, our primary objective is to shift from gathering data to uncovering the actual source of our variance. We start by using the 6M root cause framework to brainstorm potential factors across the entire manufacturing floor. As you can see, we systematically break down variables into manpower, looking at training gaps and machine, analyze tool wear or loose CNC clamping, and also method, evaluating SOP complexity. We then balance this by scrutinizing our material consistency, checking our measurement tools for operator bias, and factoring in mother nature, such as ambient temperature, changes, or floor vibration. This ensures we don't leave any stone unturned before tested our data. Once we identify potential variables, we use the 5 whys technique to drift beneath superficial symptom down to the systematic issue. Take a look at this real-world case tracking post-shipment metal tray corrosion. The initial symptom was a thin zinc plating layer. Asking why repeatedly tracking the issue through insufficient tank time and unauthorized line speed increases, all the way back to the operator trying to hit an unrealistic shift volume target. Ultimately, we uncover our true systemic root cause. Process schedules are being managed completely independent of verified machine capability limitation. Fixing the tank line speed is just a temporary bandage. Fixing the scheduling system solves the defect permanently. And brainstorming gets us theory, but Six Sigma requires statistical proof. These validation metrics act as our engineering roadmap for testing our hypothesis. Depending on our data types, we pair the specified process variable against the output effect. For example, when comparing a discrete variable like shift A versus shift B against a continuous output like yield strength, we run a two-sample t-test. If we are evaluating multiple cutting stations, we scale up to an ANOVA. And finally, if we are evaluating purely discrete parameters, such as vendor selection versus a simple pass or fill rate, we run a chi-square test. These metrics ensure every single root cause we claim is backed by mathematical certainty. And as we look at the data, we apply the presentation principle highlighted on the left. 80% of our process failures trace back to just 20% of our root cause. In an engineering environment, attempting to expend capital fixing every minor problem is highly inefficient. Instead, our action steps dictate that we rank our failure modes by cost and frequency. Draw a cumulative Pareto curve and ruthlessly target the Witter field on the left side of the chart. By eliminating those critical heavy hitters, we maximize our project ROI and achieve the massive quality gains we target in our charter. So to close out the analyze phase, we establish our exact mathematical decision boundaries through hypothesis testing. The top block details our null hypothesis, H0, which assumes the proposed root cause has absolutely no statistical effect on process variance, and the middle block set our alternative hypothesis, HA, asserting that a significant relation does exist. Most importantly, look at our decision threshold at the bottom. We only reject the null hypothesis if our calculated p-value drops below 0.05, which is the alpha. These mathematical rules ensure that we only advance to the improve phase when we have a 95% confidence level that we are fixing the correct variables. And now we are moving to the improve phase. Moving into improve phase, our immediate focus shift to action. The goal here is to build a diverse portfolio of potential solutions before locking in our final execution path. We utilize 3 core pillars. First, cross-functioning brainstorming sprints to bring floor operators and engineers together. And second, industrial benchmarking to adapt proven best-in-class methods from sister facilities. And finally, feasibility screening to rigorously filter these ideas against technical limits and budget realities. To remove guesswork from our selection process, we evaluate our ideas against standard baseline criteria using these PARC metrics. As shown in the matrix, while solution A, full automation improves cycle time, it penalizes us heavily on upfront cost and complexity. Solution B and C, which focus on target SOP rewrites and physical tooth redesigns, both yield a net total score of +3. This clear metrics logic guides our decision on which solution to move into the pivot stage based on available resources. And before rolling out changes across the entire factory, we minimize institutional risk via a pivot scale implementation. We execute this in 3 highly controlled steps. First, we deploy small-scale trial runs restricted to a single production line or shift. Second, we perform performance verification by gathering immediate continuous data to verify the fix works. And third, we focus on risk mitigation to catch any unexpected side effects before full-scale deployment. And to find the absolute best operating window for the process, we look at the mathematical model behind design of experiments. The core formula in the center show how multiple input variables and their hidden interaction mathematically determine our final product output. Why? The massive advantage here is that we move completely away from the slow traditional approach of testing one factor at a time. DOE pinpoints our optimized target parameters in far fewer trial runs, saving massive amounts of engineering time and materials. And to lock in this improvement permanently, we implement lean pokayoke, or mistake proving mechanism. On the left, we prioritize prevention, the highest value strategy, where the physical design makes errors impossibly, such as creating asymmetric component nest. On the right, we back this up with detection system, using automated optical or limit sensors that immediately halt a CNC press brake cycle if a component is misaligned. This ensures defects are stopped before they can even be created. And so we are moving to the control phase, which is the last phase. Moving into the final phase of DMAIC, the control phase, our absolute priority is locking in the gains we achieve during the improve phase. We execute this in 3 highly visual steps shown here. First, we update our SOPs immediately. If improvements are not explicitly documented, they will be lost. Second, we establish visual control on the plant floor by placing color-coded guides and physical boundary limits directly at the workstations. Third, we drive operator retraining with formal walkthrough across all shifts to ensure the new standards become daily habit. To ensure the process stays stable, our core strategy shifts away from traditional reactive end-of-line inspection toward proactive real-time monitoring. Under our control chart rules on the right, we track our critical parameters using live charts. By establishing mathematical threshold, specifically our upper and lower control limits set as plus or minus 3 sigma, we create an early warning system. Operators can catch non-random trends and intervene to adjust the machine before a single piece of scrap is ever produced. A project is only successful if it can be sustained long-term without the core project team. This metric details our official ownership handover. We have explicitly tied each key deliverable to a long-term target standard and a documented floor owner. The updated process control plan is logged under version 2.4 and handed to the floor quality lead. The new visual SOP are signed off by the manufacturing line supervisor. And finally, our plant financial controller has officially verified an annualized saving of 145,000, concluding our project closeout. However, if a process does happen to shift, we do not guess the fix. We follow a strict out-of-control action plan, which gives floor operators a step-by-step troubleshooting roadmap. And step 1 triggers the moment of SPC, chart flags an anomaly. Step 2 requires the operator to immediately quarantine all parts produced since the last verified check. And step 3 utilize our standardized checklist to diagnose common culprits like tool wear or freight pressure. And most importantly, step 4 set a hard rule. If the issue cannot be resolved within 15 minutes, it is immediately escalated to the high area engineer. To wrap up the control phase, let's look at the mathematical reality behind long-term production. In engineering, processes naturally drift over time due to tool wear, ambient temperature variations, and material changes. To account for this, Six Sigma introduced a 1.5 sigma mathematical adjustment when calculating long-term performance. This means a process operating at a short-term Six Sigma level naturally builds in a buffer, resulting in a long-term yield target of 3.4 dPMO. This standards accounts for real-world variation and ensure excellent quality over time. In a nutshell, we'll make a conclusion for the whole slide. To conclude our DMAIC journey, let's review the hard number in our project performance roll-up metrics. As the table clearly illustrates, this project has delivered measurable, statistically validated improvement across all 3 critical operation dimensions. First, in terms of quality, we crushed our project defect rate from a punishing 14.2% down to less than 0.4%, netting a massive 97.1% reduction in factory scrap. Second, our first-time yield advanced to a near-perfect 99.6%. And finally, we optimized speed, trimming our assembly cycle time by 44 seconds, meaning our line is now 31% faster. We didn't just meet our charter targets, we established a new benchmark for operation excellence. But the ultimate test of any Six Sigma project is its longevity. As highlighted on the left, we have achieved over 655 days of verified process stability. This wasn't a temporary spike in performance. Looking at the path forward on the right, this project succeeded because of 3 things. First, a fundamental culture shift where the floor team moved away from daily firefighting toward data-driven prevention. Second, complete continuous ownership, meaning our local operators actively manage the SPC charts to stop process drift immediately. And third, our next horizon, where we will now use this successful deployment as the official engineering blueprint to scale these exact DMAIC methodologies across all adjacent manufacturing lines. Thank you. And these are the references that we use for this presentation. That's all for my presentation today. Thank you.